And we're back. I don't really remember what we were doing before, but we've got some output, some odds ratios for Model 2. That's exciting. Just looking at these confidence intervals we have here, basically you don't want those to include 1. So predictor 2 does not include 1, and predictor 4 does not include 1. So those are significant odds ratios, if you will. And predictor 2 is a value less than 1, so that means that it's associated with the odds going down for enrollment. So like as predictor 2 goes up, kids are less likely to go to school, which is bad news. Predictor 2 is bad news. Predictor 4, good news. 3.73. As predictor 4 goes up, kids go to school. Good job, predictor 4. About 3.7% even. Look at you, predictor 4. Awesome. If only we could remember what you actually are. Anyway, so yeah, we're almost, oh hey, 8.5 hours now. Cool. Waking up like I'm gonna sleep. Okay. So yeah, from there, it's kind of cool because our next thing to do is conduct a hierarchical logistic regression, which I did not actually do in this syntax. This is the end of my syntax. There's no regressions even being calculated. What the hell? What did I do? Well, we already calculated 2 regressions, and we can look at those in steps. And that's pretty much what hierarchical logistic regression is going to be, just comparing those 2 steps. So we have model 1, which had the predictor of predictor 1, and we have model 2 that had predictors 1 through 4. So if we look at model 1 as a baseline and compare it to model 2, we can see if predictors 2, 3, and 4 added any additive prediction over just including predictor 1. Now going through this, I realize this is a silly example because predictor 1 was not significant and model 1 was not significant, but just for the sake of going through this, going through the motions of a hierarchical logistic regression is definitely conceptually relevant. So first line we have here is going to push into deviance change. And remember before, when we calculated those models, we got these deviance values, and when we were looking at the chi-square distribution to check significance, we were checking the deviance of the model compared to the null deviance, which is like if it were 0 basically, or yeah, null. So this time we're going to use model 1 as the comparison and subtract model 2's deviance. So we're doing the exact same thing we did before. We're just using model 1 as the base and model 2 as our thing that is being compared to the base. Yeah, cool. Let's run that. Now we have this deviance change thing. Sweet. It's really similar to chi-square 2. That makes sense because this is such a small number. It's just the difference between these two things. Cool. So that's our change in deviances. I mean, change in chi-square distributions basically. And now that we have that new chi-square distribution, we can calculate a new degrees of freedom, and in order to check the statistical significance by getting a p-value of that, we need the degrees of freedom first. So get a new degrees of freedom. It's going to be just like we did before, except that model 1 is the base. So degrees of freedom of model 1 minus degrees of freedom of model 2. It's going to be 3 degrees of freedom. And we're going to calculate a p-value based on those new values we just calculated. Kaboom. That's a pretty small p-value, definitely less than 0.05. So we could say that, yeah, Model 2 did add something on top of Model 1 that Model 1 did not have, which, again, in this scenario was kind of obvious because Model 2 was significant, Model 1 was not. But that's not really the point. The point is that that is how you check hierarchical logistic regression. And even if Model 1 was significant, we'd be able to tell if this added anything on top of that. Cool. So that's everything we've got here for logistic regression. I sure am glad to be done with this video, and I hope you are too. See you next time.